Welcome back to ECE 320A. This is the active filter unit, or unit 11, and in this video what we want to do is just explain the formula for computing the order of a Butterworth low-pass filter based on somebody giving you particular design specifications. Or how do we actually decide what this order is, n equal 1, n equal 2, n equal 7. How do we determine the formula, or how do we decide what order of filter we want for the Butterworth filter? And we will actually simply utilize the formula given to us or derived in the book. It's an approximate way to find the order, but it's very good if A sub s provides the appropriate amount of attenuation. Here's the formula that we want to use to determine the filter order, and I've tried to indicate some of the pieces that make up this particular formula. A sub s is the amount of attenuation that we need at our stop band frequency. Somewhere in the stop band, we will say we want to be at minus 25 dB by omega sub s equal to some particular value. Omega sub p is our pass band frequency. That's the minus 3 dB frequency. And n will be the filter order. And in this particular formula, it may so happen that n is not an integer. And generally it won't be from this combination of terms. It won't be an integer, and so we'll have to round up to the next highest integer value since we don't design filters of 1.7 order. We have a first order, we have a second order, we have a third order. So n needs to be an integer. As I said, this approximation is good when 10 raised to the minus 0.1 a sub s is much bigger than 1, where a sub s is in dB, and a sub s will be a negative dB, and that means really that this is a good approximation when a sub s is much smaller than minus 10 dB. So if we have something that's minus 20 dB by the stop frequency, the stop band frequency, then this approximation for determining the filter order, the Butterworth filter order, will be appropriate. Here's the diagram. And it always, I think, helps. This is actually the frequency axis. And the way that we've drawn it, it's actually log of omega. But there's our frequency, and then the vertical direction determines the attenuation. Omega sub p is our pass band or cutoff frequency, and that's where we are at minus 3 dB in terms of our frequency. And capital A sub s is how far down we are when we reach our stop band frequency, omega sub s. So we want to know what is A sub s. Maybe it's minus 20, maybe it's minus 47. We want to know what is A sub s, and once we are given a value for A sub s, we can immediately plug it into this formula together with our stop band frequency and our pass band frequency to determine the filter order. Let's look at an example. Suppose somebody says, I have a pass band of 2000 and I want the attenuation to actually be minus 16 dB when I get down to or out to a stop band frequency of 10,000 hertz. And I like to actually just picture this or provide myself with a sketch. So to do that, I would say, okay, I'm flat, this is a low pass, and then I'm going to be coming down, and I want to know really what's the slope of that decrease down into the stop band, and that's determined by these parameter values. In this particular problem, I've been told that here is my pass band frequency, and that's 2000 in hertz. My stop band frequency is a factor of 5 beyond that, so it's really not even a decade beyond that. Here is f sub s at 10,000 hertz, and when we get to this frequency, we want our magnitude to actually be minus 16 dB. That's what we want, or that's where we want to be in magnitude when we reach f sub s equal to 10,000 hertz. All we really need to do now is utilize the formula, but maybe before we do that, we can sort of, as a sanity check, we can check to see if 10 to the minus 0.1 times a sub s, which was minus 16, so now we have 10 to the 1.6. We want that to be much bigger than 1. In this case, that ends up being about 40, which is reasonable enough to say that's bigger than 1. That says then that we can go ahead and apply our formula, which is minus 0.05 times our a sub s, which was minus 16 in this case, divided by log base 10 of this ratio of our stop band frequency, 10,000, over our pass band frequency of 2,000. So we're really taking log of 5. And we divide that into the numerator term, and we end up with, in this particular case, n equaling 1.14. And I think you can see that n, 1.14, is not an integer, which now says, oh, we need to go one more up from that whole number part of that n value. N gave us a 1 and a little bit more, so we actually need to find, or need to design, a second order filter in order to achieve these design specifications. And we'll exceed those design specifications, but we want to exceed those rather than not meet those. This example then says that we need a second order filter in order to achieve that design specification. And that we can do by looking at table 15.1. Look at the row for n equal 2. We need one section, and it's a second order section, which we just discussed in a previous video. And we can find the different C values, and then we would have to scale those C's, frequency scale those C's to achieve a pass band of 2,000. And that pass band is in hertz, and typically our normalized filter sections are in radians per second. So just make sure you keep track of 2 pi in the right place. But that's all there really is to finding the order of a filter, a Butterworth filter. You need 3 things. You need the pass band frequency, you need the stop band frequency, and you need to know how much do I need to be attenuated at the stop band frequency.